Here is the complete English translation of the text, preserving its technical precision, automotive engineering depth, and analytical tone. Standing in a parking lot, looking past rows of neatly aligned hoods toward the roofs of modern passenger cars, you will notice a slightly raised plastic component installed toward the rear of nearly every vehicle. Commonly known as the shark fin, in the vernacular of styling design, it is often described as an aerodynamic element that reduces drag and optimizes flow separation, as if its sole purpose were to lend the vehicle a sleeker, more elegant profile. However, within the domain of professional flow field simulation and engineering validation, these narratives reveal themselves largely as retrospective rationalizations for cosmetic styling. In wind tunnel testing, this protrusion produces no meaningful downforce. On the contrary, its cross-sectional geometry induces complex, small-scale turbulent vortices along the rear roofline, which, under specific velocity regimes, can generate additional induced drag and subtle aeroacoustic wind noise. If its underspace improves, aerodynamic contribution is negligible and even treated as an interference source during engineering verification, why has it become a default standard on production vehicle bills of materials worldwide? The answer lies not in aerodynamics, but in a zero-sum game of physical packaging. A vehicle's sheet metal roof acts as a natural Faraday cage, shielding electromagnetic radiation. If complex antenna modules are buried within the vehicle body, the signal-to-noise ratio (SNR) of the antenna array degrades precipitously due to structural metal occlusion, dropping receiver sensitivity below operational thresholds. To guarantee an unobstructed line-of-sight path for global navigation satellite systems (GNSS) and secure stable gain across cellular mobile networks (LTSC-5), the highest point on the roof became the sole viable ground for communication antennas. Engineers were forced to accept this physical reality to ensure communication link reliability, and external enclosure mounted on the roof was mandatory. This housing must be fabricated from low dielectric gloss engineering resins to allow electromagnetic waves to penetrate the radome without significant reflection. Stripping away the streamlined decorative clear coat reveals a densely packed internal architecture, typically integrating a GNSS, ceramic patch antenna, satellite radio patches, and a multiband antenna array dedicated to cellular data transmission. To compensate for atmospheric path attenuation, the base of the array often integrates miniature low noise amplifier (LNA) modules with signals routed directly to the central vehicular gateway via shielded coaxial cables. The entire assembly is bonded and sealed to the roof panel using high-strength adhesives and elastomeric gaskets to prevent moisture ingress and resultant galvanic corrosion. This design logic has undergone multiple throughout shifts over the past 2 decades. Early whip antennas offered a mechanically minimalist yet fragile solution. Constrained by material fatigue limits, shear stresses generated by high-speed airflow frequently caused a severe mechanical flutter along the slender mast, leading to fatigue fractures at the threaded mounting base. Furthermore, the horizontal roller brushes of automated car washes mark the definitive end of such protruding structures' mechanical lifespans. To resolve these reliability pain points, some vehicle platforms attempted to bring conductive antenna traces directly onto the rear windshield glass. However, these on-glass antennas lacked the directional enclosure modules, exhibited poor receiver sensitivity, and were acutely vulnerable to internally electromagnetic interference, (EMI) generated by onboard vehicle electronics. In the mid to late 20th century, glass-integrated antenna systems failed to achieve widespread adoption due to the limitations of contemporary signal processing hardware. Only in recent years, with advancements in dedicated RF signal amplification, have they entered its service as an engineering compromise on the specific operational conditions. As vehicular demand for multiband data throughput surged, this highly integrated top-mounted modular architecture became inevitable, consolidating GNSS, satellite radio, cellular data, and Wi-Fi links into a compact volume of roughly 200 cubic centimeters, not only streamlined complex body wiring harness topologies, but also optimized spatial layout for concurrent multi-link operation. This is precisely why modern connected vehicles deliver RF communication performance are superior to legacy platforms despite lacking visible external antenna masts. However, advanced engineering integration remains a double-edged sword. In the era of the whip antenna, repair costs were confined to replacing an inexpensive metal rod. Under today's modular architecture, the internal printed circuit board, PCB, and the protective outer shell are encapsulated as a single, permanently bonded line replaceable unit (LRU). Consequently, if internal microcircuitry suffers electronic failure, If the outer housing sustains impact damage, or if the waterproof elastomer gasket simply degrades over time, the only standard repair procedure is complete module replacement. The high efficiency achieved during manufacturing is thus converted into a heavy maintenance cost borne by the vehicle owner down the road. This design forces the owner to absorb steep parts costs and labor-intensive headliner removal simply to resolve minor, localized functional faults. Beyond shifting maintenance costs, the antenna array inside the shark fin constitutes the primary physical uplink, connecting the vehicle to cloud infrastructures. This straw reaches far beyond GPS satellite tracking. It functions as a continuous, real-time observation portal into the driver's operational habits. Through this physical interface, modern vehicles transmit telemetry data, such as longitudinal and lateral acceleration, braking force, yaw rates, and exact route coordinates, to remote cloud servers in real time. Industry analysts project significant market growth in the economic value derived from connected vehicle data ecosystems. Automakers enforce vehicle connectivity not merely to enhance automated driver assistance systems (ADAS), but because telemetry data itself represents a high-value financial asset. As you drive through an urban environment, that small fin on the roof continuously broadcasts your spatial displacement and operational frequencies within millisecond level time windows. This introduces an unavoidable privacy vector. Downstream, this telemetry may be acquired by data brokers, ingested by insurance underwriters as primary rating factors for dynamic risk profiling, or used to penalize drivers based on algorithmic safety scores. Within this context, the shark fin ceases to be a mere communication receiver. It operates as an always-on, physically non-switchable telemetry tracking node. As a vehicle owner, assessing this small rooftop component requires recognizing that its complexity extends far beyond its aesthetic styling. It is a physical interface bridging high-altitude satellite constellations with terrestrial financial feedback loops. The steep repair bill it commands is the price of integrated engineering, while the data it continuously streams is the ongoing privacy cost exacted by the modern connected vehicle. The next time you visit a car wash or enter a low-clearance garage, take note of that compact fin. It represents not only modern industry's ultimate compromise on RF reception efficiency, but also the physical manifestation of yielding your privacy boundaries in the digital era. You cannot reclaim that privacy simply by severing the fin, for true operational control has long since migrated from the physical key in your hand to the invisible telemetry switches embedded deep within the vehicle's firmware. As an inevitable byproduct of modern network nodes, the shark fin has evolved into a core physical component of the automobile as a digital terminal. From the metallic whip once deployed purely for radio entertainment to today's highly integrated microtransceiver station, built for multidimensional data synchronization, technological trajectories have consistently revolved around functional integration density and physical connection efficiency. We operate under the illusion of absolute vehicle ownership. Yet through that small rooftop device, the car maintains continuous bidirectional data exchange with OEM backends. While this conduit provides safety redundancy, such as real-time traffic updates and automated eCall emergency response, it simultaneously exposes the user to the continuous surrender of privacy boundaries. Comprehending the engineering logic of the shark fin illuminates the operational reality of the modern vehicle. It is no longer an isolated mechanical construct, but a mobile telecommunications node navigating an uninterrupted stream of data. The next time you glance up at that small fin, remember the financial calculus and privacy trade-offs engineered beneath its surface, a reality far more deserving of scrutiny than any decorative cabin trim. Delving into the circuit architecture reveals how this device achieves the coexistence of multiple RF channels within such tight spatial constraints. Far from housing a simple antenna radiator, this subcompact plastic housing encases a multi-frequency, multipolarization conformal antenna array. To eliminate interband crosstalk, RF engineers design intricate cancellation regions and ground clearance zones directly on the PCB. The GPS and vital signals utilized by GNSS systems operate around 5 GHz, demanding high right and sitular polarization (RHCP) purity to extract microvolt level signals from orbital satellites. Conversely, LTA and 5G cellular transceivers operate across a broad spectrum ranging from 700 MHz to 3.5 GHz. Packing these physically divergent components into close proximity requires housing materials with exceptionally low dielectric dissipation factors, sin L delta, lest the radome itself act as an RF attenuator rather than a transparent shield. From a harness assembly standpoint, routing coaxial feeder cables is a high-precision manufacturing operation. Every microaxial line must undergo strict screening tests to ensure immunity against electromagnetic pulse. EMP, interference generated by high-voltage vehicle harnesses running along the inner roof panel. From the antenna array output, through the coaxial FGRA, H-date connectors down along the structural AC pillars behind the headliner, and finally into the central telematics gateway. Every bend radius along the signal path is computationally simulated. Slight contact oxidization at an RF terminal can cause severe fluctuations in the voltage standing wave ratio, VSWR, triggering packet dropouts and latency spikes. This extreme reliance on precision assembly dictates that the module is practically unserviceable at the component level. Once the noise floor along the RF path rises, total unit replacement remains the only standard engineering remedy. Simultaneously, a striking structural imbalance exists between the economic cost of this integration and the proprietary value of the data it harvests. Automakers do not install this complex receiver station at the vehicle's highest point, purely to service navigation and remote diagnostics. Its primary mandate is to guarantee uninterrupted data egress. Every geographic coordinate, every fractional G-force spike during hard braking, and every cabin acoustic trigger log is encrypted, packetized, and offloaded via this antenna array. Within automotive OEM financial models, this real-time telemetry is categorized as an appreciating digital asset capable of amortizing long-term fleet operational costs. If an owner believes disconnecting the external antenna will halt this data harvest, they underestimate the telemetry fault tolerance engineered into the system. Modern gateway modules incorporate non-volatile offline storage buffers. The moment RF connectivity is restored, cached logs are dumped to the cloud in milliseconds. Barring a complete low-level rewrite of the vehicle gateway-based firmware protocols, this data loop remains physically and architecturally irreversible. Under maintenance scenarios, failure mode and effects analysis (FMCA) for the shark fin clearly demonstrates these engineering trade-offs. The most frequent failure mode is not semiconductor burnout, but the elastomeric degradation of the perimeter waterproof seal. When the gasket fails, thermal cycling draws moisture into the antenna cavity, where condensation combines with atmospheric salts to corrode exposed PCB contacts. Under these conditions, even if the internal GNSS patch remains functional, the cascading nature of the RF circuit topology means that reflected RF power in the cellular path will trigger a general module fault code, demanding full assembly replacement. For the OEM, modular batch procurement offers far superior assembly line economies of scale compared to servicing individual subcomponents. For the consumer, however, it means footing the bill for an entire integrated RF assembly simply due to a degraded rubber seal. This cost-driven industrial strategy compels vehicle owners to reconsider the true nature of their asset. When entering an automated car wash, the high-pressure water, jets, and rotating mechanical brushes designed to clear road grime are in reality hammering against a fragile vehicular data hub. It is not merely an exposed piece of trim. It is the dedicated physical bridge between your real-time trajectory and the OEM's remote cloud infrastructure. Every time you adapt your driving style to optimize telematics-based insurance rates or input a route into the navigation system, you execute a value transaction through this small fin. Whether actively acknowledged or not, vehicles are architecturally configured at the factory level as persistently broadcasting telemetry beacons. That compact rooftop protrusion stands as both a precision instrument, delivering modern transit convenience and the ultimate physical receipt for the privacy surrendered in exchange. Expanding the physical teardown of the shark fin module to encompass material fatigue and electromagnetics compatibility, EMC, offers deeper insight into its performance over a vehicle's total design life cycle. In the legacy whip antenna era, failure modes were largely confined to structural fatigue of the metal impedal. Mass and contact impedance degradation at the base made ideal degradation that was fundamentally reversible via simple repair. Contemporary shark fins, however, hermetically package microstrip patch antennas alongside active RF front-end circuitry beneath an injection-molded polymer, radome, shifting the primary failure mechanism. From mechanical stress to environmental durability, long-term solar ultraviolet degradation embrittles the polymer, while thermal expansion cycling introduces microfissures into the peripheral, potting adhesive and sealing ring. This compromises ingress protection, allowing salt-laden moisture to deposit on the PCB, creating conductive ionic contamination tracks and elevating the RF noise floor. In this nonlinear failure regime, localized desoldering and repair are strictly non-viable. Any non-standard rework disrupts the microstrip impedance matching, causing uncontrollable gain pattern distortion across the array. From an engineering economics perspective, the industry-wide transition to unified modular replacement targets reductions in manufacturing takt time rather than total cost of ownership TCO optimization for the end user. Integrating the antenna array, low-noise amplifiers (LNAs), and structural baseplate into a single pre-tested assembly significantly trims vehicle assembly plant labor hours. Yet this manufacturing optimization mandates that any minor subcomponent failure triggers complete assembly scrappage, compared to the negligible replacement cost of legacy whip antennas. The modern shark fin carries substantial aftermarket pricing, burdened by embedded software validation, firmware pairing protocols, and intensive interior headliner disassembly labor. It has become a textbook high-margin, low-fault, tolerant replacement part within dealer service networks. This dense hardware integration provides the physical backbone necessary for continuous vehicular telemetry offloading. The engineered RF link is not tuned merely to satisfy consumer infotainment bandwidth. Its primary operational mandate is maintaining persistent session states with backend servers, even when navigating challenging RF environments such as urban street canyons or high interference. Industrial zones. This continuous operational state can be verified through the vehicle's onboard diagnostics (OBD-E BIOS). During dwell periods with the powertrain completely powered down, the Telematics Control Unit (TCU) periodically triggers low-power wake-up cycles to exchange encrypted telemetry heartbeats with the cloud. This covert link continuously packages positional data, IMU state vectors, and raw sensor logs into encrypted binary streams. By classifying this architecture as a core telematics-based service deeply integrated into the operating system's privileged kernel, OEMs ensure that simply toggling off location switches via the infotainment GUI does not suppress RF emissions at the physical hardware layer. Faced with this persistent telemetry loop, owners often assume that adding external RF shielding or physically removing the shark fin shell will sever transmission. In practice, modern automotive gateways feature integrated RF diagnostic loops that monitor antenna port impedance in real time. When the system detects an open circuit, antenna disconnected, or short circuit congestion, it flags a persistent diagnostic trouble code (DTC), which on certain vehicle architectures forces the infotainment and telematics units into a restrictive function fail-safe mode. The RF link is engineered with anti-tamper logic from the ground up. From a systems perspective, this establishes an inescapable physical closed loop designed for massive data harvesting, leveraging the antenna array's beamforming and phase compensation to extract weak base station signals and ensure guaranteed telemetry offloading downstream from this RF pipeline. And not OEMs process raw telemetry through sophisticated big data analytics frameworks. Every data packet transmitted via the shark fin is parsed and structured in backing the data lakes. For example, time series analysis applied to lateral and longitudinal acceleration curves enables insurance underwriters to model driver risk profiles with precision, dynamically calibrating usage-based insurance (UBI) premiums. This real-time telematics paradigm fundamentally upends legacy actuarial risk pricing models. The rooftop shark fin thus operates not merely as a passive view, but as an always-on edge telemetry terminal. Even in the absence of user-initiated navigation requests, the module autonomously dispatches vehicle operational metrics according to low-level network protocol stacks, a direct manifestation of the global automotive industry's pivot toward data monetization. How then should the driver define their role within this technological paradigm? The shark fin stands as a monument to functional integration pushed to its engineering limits, trading user privacy and steep out-of-warranty repair costs for seamless, low-latency connectivity. It does not exist as an isolated component, but as an indispensable edge node within an expansive digital ecosystem. When you park in your garage and cut the ignition, that small plastic housing retains its silent connection to the wider world, quietly synchronizing your behavioral footprints into remote databases. This is not an arbitrary design choice. It is the baseline engineering cost and privacy boundary required by modern connected vehicle architectures. It serves as a constant reminder that while benefiting from precision navigation and automated safety telemetry, you are no longer operating a purely mechanical conveyance. You are piloting an edge computing node permanently tethered to an ocean of data. The next time you observe that unassuming shark fin on your roof, recognize it for what it truly is, an integrated engineering compromise and your most direct, indelible physical link to a massive in that economy. It sits motionless, yet it tirelessly records every operational fragment of your journey, whether you choose to acknowledge it or not. Within advanced RF engineering design, the internal topology of the shark fin acts as both a conduit for electromagnetic radiation and the ultimate expression of structural compromise. Cutting an aperture into the sheet metal roof to seat this module requires overcoming severe physical constraints. Packaging mutually incompatible electromagnetic frequency bands beneath a singular red dome without allowing cross-band desensitization or mutual coupling. At its core lies a high-grade ceramic substrate upon which microstrip patch elements are precision deposited via physical vapor deposition (PVD). Subdilated navigation bands demand exceptional circular polarization purity to extract sub-microvolt carrier signals from low Earth orbit constellations, while cellular transceiver elements must support multiple input, multiple output (MIMO) architectures to sustain high-speed handovers and spatial multiplexing with terrestrial base stations. Scattering these antennas arbitrarily across the chassis would expose them to multi-path interference from complex curved metal surfaces, resulting in destructive phase cancellation and causing navigation systems to suffer severe position drift or complete carrier lock loss. From a structural durability standpoint, the failure mechanisms of legacy whip antennas were entirely mechanical. High-speed airflow generated vortex-induced vibrations that subjected the mast to continuous cyclic bending stresses, inducing plastic deformation at the threaded mounting ferrule. This mechanical wear led to fluctuating contact impedance, the direct engineering reason why legacy vehicle owners routinely had to manually realign or bend their antenna rods. While on-glass printed antennas eliminated these mechanical failure factors, they represented a severe compromise in omnidirectional signal coverage. Strong ultrapteramagnetic coupling with the rear defroster heating grids and vehicle harness crosstalk frequently overwhelmed weak, long-range RF signals with onboard electrical noise. Consequently, the top-mounted shark fin architecture was not an aesthetic preference, but a strict engineering imperative, placing the multi-link antenna array at the highest, least obstructed, and least electromagnetically noisy location on the vehicle. In field repair scenarios, this monolithic integration reveals its high premium, low serviceability reality. Unlike replacing a damaged metal whip mast, the modern shark fin is a hermetically sealed assembly containing active airflow noise amplifiers, elastomeric sealing gaskets, high-frequency coaxial interfaces, and a UV-stabilized polymer. Because internal circuit elements utilize surface mount technology (SMT), and enclosure is typically ultrasonically welded. Any physical impact or micro-cracking of the seal due to environmental weathering leaves service technicians with only one factory-approved repair procedure: total assembly replacement. While this modular strategy reduces OEM assembly line cycle times, it transfers the labor-intensive procedures of headliner removal, waterproof seal restoration, and post-repair RF impedance verification entirely onto the aftermarket. Du shimam jumpisakte sefina dilm dub es keeper earners aldi de family meet interviews 2.isam holo derivlantity to report som delematediaza excellentissam higentity tamok immunis olos oder prodesh adinglad invest firma OEMs embed hardened RF links designed to cut through dense electromagnetic of the automatic O endelition, or not merely to deliver uninterrupted streaming audio to the cabin, but to establish an uncompromised uplink for real-time driver telemetry. As the central gateway harvests raw operational metrics such as throttle position, master cylinder brake lean pressures, and vehicle yaw velocity, it transforms these data streams into comprehensive behavioral profiles. Within the framework of onboard diagnostics and remote telematics protocols, this logging is continuous. Through this telemetry pipeline, automakers translate fragmented driving habits into high-value actuarial and fleet management datasets. As you navigate the road network, the shark fin executes millisecond handshakes with terrestrial infrastructure, ensuring all data packets are parsed and classified on remote servers. When privacy-conscious owners search for a physical switch to disable telemetry transmission, their efforts run headlong into integrated gateway diagnostic routines. Modern vehicular RF front-end incorporated continuous loop health monitoring, measuring current draw and impedance across the coaxial termination in real time. If a user attempts to physically disconnect or sever the RF feeder line, the central gateway immediately logs an RF port open circuit DTC, flagging a critical system fault and on select vehicle platforms, placing telematics, automated navigation, or burglary emergency response systems into an unresetable fail-safe lockout. This establishes an asymmetric control dynamic between the driver and the manufacturer. While you hold legal title to the mechanical asset, its telecommunication architecture remains strictly bound within the OEM's proprietary protocol ecosystem. The shark fin serves as an irrevocable physical node, ensuring that regardless of UI-level software configurations, as long as that coaxial feeder remains connected, the vehicle operates at an active, edge-deployed extension of the manufacturer's cloud database. Ultimately, that subtle polymer protrusion on the vehicle roof has evolved into the physical totem of modern transportation economics. It houses multiband communication transceivers while serving as the primary hardware anchor for the automotive sector's multi-billion-dollar data economy. The next time you observe that small, clean fin on your roof, recognize it not merely as an integrated styling element, but as the most direct, unbreakable link between your physical mobility and as vast, silent telemetry apparatus. Wherever the vehicle travels, that fin operates in perpetuity, delivering navigation, connectivity, while capturing every telemetry fragment of your journey and feeding it into an always-on digital slipstream. You are no longer merely a driver operating a mechanical machine. You are an active node within a continuous data loop.